So this is probably not the single hardest concept of computer science, but this is a topic that is taught so early and comes up so often in these interview questions that it was just a huge struggle when I was studying for these interviews. And the topic is recursion. Honestly, anytime I got a question about recursion, I would immediately be like, fuck. And now before you say this is literally taught in every single computer science class, well, I didn't really pay attention, okay? And this goes out to all the people like me. Now let me preface by saying you shouldn't necessarily do this method in an actual interview unless it's asked for, but rather it's supposed to improve your visualization and intuition of these questions. All right, so here we have the most basic recursion function, the Fibonacci sequence. And if you don't know what this is basically a sequence where each number is the sum of the preceding two numbers. Let me show you an example real quick. So for this example, we'll define the first Fibonacci number as 1, where each number is the sum of the preceding two numbers. And over here, we have our Fibonacci sequence defined in code, where if we call Fibonacci of 1, we'll get 1, and if we call Fibonacci of 5, we'll get 5. So the hard part for me was always visualizing recursion in my head. Like, I would always try to keep track of all these numbers that are being returned. I would try to like write them down on the side, and then at some point I would come up in the recursion tree and lose my place and my values. It was kind of a mess, and it just made me really afraid of these recursion type problems. So the trick here is to keep track of the recursion in a tree-like structure. Let me explain. So say we're trying to find the fourth Fibonacci number right here, which is 3. So let's visualize this with a tree structure. So we'll begin by starting with our input of 4 into the top level function. And we can see here that 4 fails the conditional right here because it's not 1 and it's not 2. So we pass this and we go on to the first recursive call, which is Fibonacci of n minus 1. So now we define this as a new branch in the tree. So now we are in a brand new function call with 3 as the input, 3 being n minus 1 from above. And at this point, we've entered a brand new function call. And we can see that it does not pass the conditional. So we move on to the recursive step again of Fibonacci of n minus 1, which is 2. And we see here now that 2 indeed does pass this base case because n is equal to 2. So this is where we have to exit early from the function and return 1. And this is where we start tracking our return values up the tree. So now I add in the return value, which is 1. And so now we're back in the function call for the input of 3. And we've already done the left side of the recursion and gotten a return value. Now we have to do the right side, which is Fibonacci of n minus 2, which is 1. And now we see this again passes the conditional, and we again have to exit early out of this function. So let's track the return value. And now for this previous function in the tree, f of 3, all recursive calls have been completed with their return value. So all we have to do is add together the return values we got from the recursive function and return it to the calling function. So we have 1 and 1, which is 2. And now the rest of the recursive function will continue similarly. And now that we have this final recursive call completed, we have everything we need in the original function to calculate the Fibonacci number, which is 2 plus 1, which is 3. And that is our final solution. So now that you see how all this is done, you realize you don't need this complicated code structure in this tree here in order to do this in your head. You can just replace them with simple markers instead. This is the way I usually visualize the exact same structure in my head. I recommend when you get started with recursion, draw out this tree for literally every single recursion question you do, because it will really drill in your intuition and your visualization. This technique really helped me a lot. And trust me, I was really bad at recursion. So this strategy can be applied to all kinds of recursion questions. Permutation, backtracking, dynamic programming. The more you do, the more you'll be able to visualize this tree structure in your head. And you'll feel much less stress when these kinds of questions come up in interviews. The other thing is it's actually great for checking your work and showing to an interviewer that your code actually works. And you can also use this same technique to really visualize where the repeated work or memoization is happening in your recursion function. So as you can see here, I've drawn out the recursion tree for Fibonacci of 5 rather than Fibonacci of 4. And you can see it's a slightly larger tree. And you see right here that f of 3 is called twice, with each of their subtrees being identical pretty much. So in terms of time for this small tree, it really doesn't matter that much. But what if you increase the time complexity and say you're trying to calculate f of 100 or something? Now suddenly the amount of repeated calls you're doing increases exponentially. So memoization visualized is basically calculating all these values once and caching them so that you don't need to do the repeated work. So if you see here on the left, I have an array. So every time you call a function and calculate its result, you store it in this array and pass it between your function calls. For 3, I've already calculated it as 2. And then the next time I see an f of 3, I completely eliminate all the recursive subwork, saving you extra work and time. So I know for some people drawing out this tree might seem dumb, but man, if you ever had the feeling of doing recursion without knowing this method, your brain literally feels like that meme where you're just stuck and you have nowhere to go. And after I did this concept enough times, it really reduced the amount of stress I felt during these interviews. Hopefully this helped you too.